think I'm, oh, 2 minutes late. Late. Okay. Now, I hope everybody watched Saturday night that our Indiana Pacers beat the Miami Heat, forcing a 7th game. I think it's tonight. So you probably weren't doing any homework. Let's get back to portfolio theory. Let's take one of these pens. I think we're session 5. And today we're going to do some interesting stuff. And exactly, we're going to look at the diversification results. We alluded to these before, but let's actually make some derivations here. Let's start with a portfolio of 2 assets. And we can call these A and B. I think before we called them X and Y, but that's okay. And assume that we invest a proportion WA in A and WB in asset B. Okay. So WB equals 1 minus WA. Because we're going to use our whole budget. Otherwise, if we don't, we're just getting zero money on part of our budget. Although some people keep cash in their budgets. Here, we're not going to allow that. So first we look at our portfolio. Expected rate of return. And we say the expected value of the portfolio rate of return, RP, equals WA times the expected value of RA plus WB times the expected value of RB. So this is linear in WA and WB. In fact, you could say it's linear in WA because we can express WB as 1 minus WA here. Now, let's derive the portfolio variance. Before we stated that, but we didn't derive it. Okay, so first of all, let's define it. The portfolio variance is the expected value of what? Of WA, RA, minus, let's say plus WB, RB, okay, that's the portfolio's expected rate of return, and we take that minus WA, R bar A, plus WB, R bar B. Now this is the portfolio's expected return. These are just the values, and we square this whole thing here. Now let's gather A and B terms. So now this is going to equal what? It's going to equal the expected value of WA, RA, this is a plus here. It looks a little screwy to me. There's a plus here too. Minus WA, R bar A, plus WB, RB, minus WB, R bar B. And we square this whole thing. Okay. Now, let's look at something. Is WA minus RA minus WA R bar A, let's say that that's analogous to X. Now let me say WB R bar B, RB minus WB R bar B is analogous to Y. So we have something that's analogous to the expected value of X, and this is squared, X plus Y squared here. Okay, and when you run this out, X plus Y squared, what do we get? Let's look at that. So we're looking at the expected value of X plus Y squared. Let's do that here. The expected value of X plus Y squared, we all know, is the following. Equals the expected value of X squared plus 2XY plus Y squared. Okay? Okay, so now substitute our portfolio terms we could say asset terms for X and Y. Okay, if we do that, then we get a nice expression here. And we get sigma p squared equals what? Equals the expected value, because we still have this guy sitting around, of what? Of WA squared times RA minus R bar A squared. That's our X squared terms. And we have our 2XY terms. We get plus 2WA, WB, RA minus R bar A times RB we're just about going to have enough room here, minus R bar B. Okay, plus what else? Plus WB squared RB minus R bar B. Okay, squared. Okay, so this is our x squared term. This is our 2xy term. And this is our y squared term. Okay, so what we've done is just complete the squares. So we just have a little more complicated than our x squared plus 2xy plus y squared. Okay, now what do we know? We know RA minus R bar A squared is what? That is the, and the expected value of that is what? That's the variance about the return of A. So let's substitute that in. So this is a nice derivation. So sigma p squared equals what? We take the expected value of this first term is what? Is WA sigma A squared. Of the second term, we have RA minus R bar A times RB minus R bar B. This is just our covariance plus 2 WA WB sigma AB, that's the covariance there. And likewise, the expected value of this is just plus, this should be WA squared, excuse me, WB squared sigma B squared. Okay. So this is, we stated this equation for the portfolio variance for two assets, but now we've derived it. Okay, so now let's take away this covariance, and let's express it in terms of the correlation coefficient. So this equals what? WA squared sigma A squared plus 2WA WB. Okay, now we're going to express that in terms of the correlation coefficient, rho AB, sigma A, sigma B, plus WB squared, sigma B squared. Okay, so now we have it in terms here of the correlation coefficient. So now we can tell what happens for different values of the correlation coefficient. So let's go on here. The next thing we're going to do is a numerical example. So those derivations are very important because they show what that shows what a portfolio of two assets. Now let's do a numerical example. And we're going to show how adding assets or stocks, or if you're a firm, looking, let's do this, projects, if you're looking to minimize your risk here, the firm can think of things like, instead of picking a portfolio of stocks, pick a portfolio of projects that it wants to do. So we want to see how adding assets can actually reduce portfolio variance which is a sigma p squared if the assets are uncorrelated. In other words, we have that rho AB equals rho BA equals 0. Also, we have that sigma squared AB equals 0. Obviously. Okay. Now, let's look at a specific example. Let's look at some numbers. So we want to see how adding assets can reduce the portfolio variance if the assets are uncorrelated. Suppose we have the following data. And we have that sigma a squared equals 9. So sigma a, the standard deviation, equals 3. We'll pick some real easy numbers here. Sigma b squared equals 16. So its square root, which was the standard deviation, sigma b, equals 4. Okay. Okay. Now, let's do the following. Let's start with and you could call it a trivial or completely undiversified portfolio consisting of solely one asset, say asset A. You can think of this as a stock, of course. A. And let's add a riskier asset to A, and we'll call that B, to A, to form another portfolio. And we say that B is a riskier asset here with Oh, we're getting too low here. Let me see if I can't move it up a little bit. Okay, good. With 1/2 of our funds in each asset. So now we split our portfolio half and half between A and B. Okay, let's see what we have now. And recall that we have sigma A squared equals 9, sigma B squared equals 16. Sigma A equals 3, sigma B equals 4, and we have rho AB equals rho BA equals sigma AB. No, we don't want that. What's this? Yeah, we can have that. Equals sigma AB equals sigma BA, because now we're totally uncorrelated, equals 0. Typically, rho AB is not equal to sigma AB, not equal to the covariance, because covariance could be any number. Remember that the correlation coefficient has to be between -1 and 1. Okay. And we have WA equals WB equals 1/2. Okay. So now let's calculate the two asset portfolios variance sigma p squared. Okay, so we see, what do we see is that B is riskier than A. I don't have much space here. I apologize. Okay, so the asset that we add to our portfolio has a variance of 16, where our original portfolio only had a variance of 9. Let's see what happens. Let's calculate that. And this is a nice numerical example here. Sigma p squared, we say now, sigma p squared equals what? Equals WA squared sigma A squared plus WB squared sigma B squared plus 2WA WB rho AB sigma A times sigma B. We just about got that in there. Okay. So what does this equal? We have an equal part. So let's look at this. This is WA is 1/2. And we square that. Sigma A squared, we know what sigma A squared is 9. Plus, what do we have? WB squared is also 1/2 squared times sigma B squared. Remember, that had a higher variance, and that's times 16 here. Okay. Okay, now we have this whole term, but what happens here? We said that sigma AB, this goes to 0. So we have plus 0 here. So our combined term goes to 0. Okay, so let's look at this. What do we have? So this equals 1 quarter squared is just 1/4. So this equals 9/4 plus 16/4 equals 25/4. Okay. Which equals 6.25. Now this is less than sigma A squared equals 9, and it's also less than sigma B squared equals 16. So what we've done is we've added a riskier portfolio to another portfolio and actually reduced the portfolio risk here below either of the assets. So this really shows you the power of diversification. Now, given here we have the assets are totally uncorrelated. It's very hard to find totally uncorrelated assets or assets that are perfectly negatively correlated. Typically, assets are somewhat positively correlated. So our conclusion is the following, is that, so adding a riskier asset such as B can sometimes reduce our portfolio risk as measured by our variance below the risk of any of the assets in our new portfolio. And in fact, as in our example, demonstrates. Well, we're running out of space there. Okay, because we got sigma p squared equals 6.25, and 6.25 is less than sigma a squared equals 9, and it's also less than sigma b squared equals 16. So adding that b, which is a riskier asset, to asset A, actually reduced our portfolio variance below the risk of any asset. Now, this is because we have the two assets are uncorrelated, which is hard to come by. Okay. Now, let's get on to some results here. Good. Good. However, diversification cannot reduce risk So we can't reduce portfolio risk if the assets are all perfectly positively correlated. So we would say that sigma ij squared equals sigma ji squared equals 1 for all I not equal to j. Likewise, we could say that, in terms of the correlation coefficient, what we'll usually be working with is that rho ij equals rho ji. No, we don't need this. This is wrong. I'm sorry, because it's sigma. The variance of the covariance doesn't have to equal 1. It has some number. So let's take that off. Sigma ij equals sigma ji equals 1 for all I not equal to j. Okay. So now we have things that are perfectly positively correlated. And here we can't reduce portfolio risk, we say. So let's do an example. Let's do a numerical example. Because the numerical examples are a lot nicer, I think, than just doing a theory. Yeah. Okay, our numerical example, notes are missing a page. Let's take one that, let's do sigma a squared equals 9, as before. But now, let sigma b squared equals 9. So now we add an asset that has exactly the same risk as A. And we're going to let WA equal WB equal 1/2. So again, we start with A, then add B to form our portfolio. So let's see exactly what our portfolio variance is. Our portfolio variance is the following. Sigma p squared equals what? Equals WA squared, sigma A squared, plus WB squared, sigma B squared, plus 2WA, WB, rho AB, sigma A, sigma B. Let me bring this down a little bit. this is a row. It's not a parenthesis sign. Okay, so now let's plug in our data here. That this equals what? Equals 1/2 squared. This is WA. This is WA squared times 9 plus 2. Now we'll get this term here. Let's not get that term first. Let's do this. Let me do mine a little bit differently. Plus 1/2 squared times 9 again. This is for WB squared. Plus, let's take our combined term here, plus 2 times 1/2 times 1/2. Okay, we know that this is WA and WB. WB terms times rho AB, 1, times sigma A, sigma B. Okay, so we have 3 and 3. Okay, so let's just look at what these guys are. This is our rho AB. This is sigma A, and this is sigma B. Okay, so what do we have? This equals what? Now let's put our equals over here. Equals 9/4 plus 9/4 here, because 1/2 squared is a 1/4, so we have 2 9/4 plus, what do we have here? Let's look at this. We have 2 times 1/2, so we can cancel these terms. So what do we have? We have 1/2 times 9. So that's 9/2. 9/2. And what does this equal? This equals exactly 9. Equals sigma A squared equals sigma B squared. So if our assets are perfectly positively correlated, then adding another asset cannot reduce our portfolio variance here. Now, very seldom do we have perfectly positively correlated assets here. Now, let's look at some other diversification. Oh, let's do another example. Let's see what happens to portfolio variance. Why don't we call it risk? Sigma P squared. If assets are perfectly negatively correlated. Okay. Again, let's assume that sigma A squared equals sigma B squared equals 9 So sigma A equals sigma B, the standard deviation, equals 3. Just equal to square root of 9. And assume we start with a single asset A, then add B to form a new portfolio. So we start with a portfolio consisting of precisely one asset. Then we want to add another asset to it. Okay. And now we have and we want the two assets to be perfectly negatively correlated. So this is rho AB equals -1. Okay. So we're going to see a neat thing here. If you could find two assets that are perfectly negatively correlated, you'd be doing great. Let's see why. Now, the two asset portfolio variance is what? Sigma p squared equals, again, our old expression WA squared times sigma A squared plus WB squared times sigma B squared plus 2WA WB rho AB sigma A sigma B. And now we're going to have this rho AB equals -1. Okay, so A and B are perfectly negatively correlated. Now, it's almost impossible to find two assets that are perfectly negatively correlated. You could look at sometimes if you looked at, say, the price of gold and the Dow Jones, sometimes they're negatively correlated, but not necessarily, but not perfectly. But you can see that the price of gold has dropped significantly from a high about 1,800 to around 1,400 an ounce, where the Dow has been on a bull run here. And it's yet to be seen how the Dow does, especially when we get disturbing news about the Nikkei going down. Okay, so let's calculate this. This equals 1/2 squared times sigma A squared equals 9 plus 1/2 squared times 9 again, sigma B squared, okay, plus 2 times 1/2 WA times 1/2 WB times -1 rho AB times 3 times 3. So again, take the 2 and the 1/2 off, and what do we get? Here we get 9/4 plus 9/4, and we have this -1 here, minus 9/2. And so now our portfolio risk equals precisely 0, equals 9/2 minus 9/2. So if you have two perfectly negatively correlated assets, we can reduce portfolio risk to zero sometimes. Now, let's see, and we just looked at small portfolios. Let's see what happens if, let's extend this to n assets and see what happens as n goes to infinity. To n assets. And we could have said greater than or equal to 2 assets in our portfolio. Okay, so it's a straightforward extension here. We say the expected value of our portfolio rate of return is just equal to the weighted I equals 1 to n WI expected value of the rate of return of asset I. Okay? So this is linear again. And now we have the following. Sigma p squared equals what? Equals the sum I equals 1 to n WI squared sigma I squared. So these are the terms when I equals j. When I equals j, sigma ij goes to the variance here, plus the double summation I equals 1 to n, j equals 1 to n, and it also must be true I not equal to j. So in fact, this term here is when I equals j. So we have our variance terms, then we're going to have our covariance terms. Wi, wj, sigma ij. And as before, we can always express sigma ij, if we like, by rho ij times sigma I, sigma j. And this, of course, is from the definition of rho ij. Equals what? Equals sigma ij over sigma I times sigma j. So then sigma ij just equals rho ij times sigma I times sigma j. Okay, like we said before. We're just using the definition of the correlation coefficient. Okay, let's see how far we can get. Now, let's see what happens to our portfolio risk as the number of and this is the number n of assets, increases. Okay. Let's, for simplicity, let Wi equal 1 over n. So all assets are equally weighted in our portfolio. Okay. This is I equals 1 to n. And first, let's consider the case of uncorrelated assets. Okay. And here we have rho ij equals rho ji equals, that's sigma ij, rho ij equals rho ji equals 0. So they're perfectly uncorrelated here, assets. Okay. What are we doing here? Let's see, we can do a couple more things. Okay. Good. So now we have sigma p squared equals what? First we gather all terms, all variance terms. I equals 1 to n, wi squared, sigma I squared. These are all the terms where I equals j. Okay. When I equals j, we just get the covariance equals the variance. Plus what? Plus our double summation here. Summation I equals 1 to n. J equals 1 to n. And it must be true here that I is not equal to j. So here I is not equal to j. So when I is not equal to j, we get some covariance terms. Is what? wi, wj, and let's see how much space. Okay, we can do this. Rho ij, sigma I, sigma j. Okay. Now, rho ij is what? We're negatively correlated. So this equals 0. Or this equals minus 1. What am I talking about? No, this equals 0. We're talking about 0 is uncorrelated. Rho equals 0 or uncorrelated assets. Good. Okay. Uncorrelated assets. So if rho equals 0, this whole term, so now we just get the variance term. I equals 1 to n, wi squared, sigma I squared, plus 0. The I not equal to j term goes to 0. Okay. And so we can express this as the following, as 1 over n, because this is 1 over n squared, right? Here, this is 1 over n squared. Here, times the sum of what? Of I equals 1 to n, sigma I squared over n. Now sigma I squared over n is what? This is just the average variance, or mean variance. And we'll call it average asset variance here. Now the limit, the key thing in here is that, let's see if we can just write down one more thing today. The limit as n goes to infinity, our number of assets go to infinity, of sigma p squared what do we get? Equals the limit as n goes to infinity of what? 1 over n times sigma bar squared, right? That's our average asset variance. And if you, as n goes to infinity, this term goes to 0. So all risk can be eliminated. So if you have uncorrelated assets, life becomes very easy. You can eliminate all possible risks here as the number of assets gets larger and larger. And we had a numerical example before where we said that. Now, next, and I think we're going to be out of time now. We are out of time. Okay. What happened to the music, guys? We're supposed to have music before. Okay, thank you very much. We'll see you tomorrow.